There. Now the audio is working. Okay. Let's start by reflecting a little bit on how insane 161 was in terms of what you learned. Raise your hand if you had no programming experience before 161. Okay, so basically everybody. That often, for better or worse, ends up being usually a good thing. A lot of people that come with previous experience, with people coming with experience programming, for some reason, anecdotally, tend to not do as well for whatever reason. So this course assumes you know nothing. And it starts at Hello World, right? It starts at print Hello World. You've never written a line of code before, or maybe you've done something equivalent to like a Hello World. And you did Hello World. The end of the semester, you're making classes and objects, and we're talking about sorting algorithms. We covered a lot. Like, it's insane how much. Go back 3 months from now, and I ask you to solve the most basic thing, and you'd look at me like I'm crazy. Like, what? I can't write a function to convert Celsius to Fahrenheit. You'd be like, 3 months ago, you wouldn't know what the hell that means. Now, I tell you to do that, you're like, that's the easiest thing in the world, right? Def, some function name, parameter, return, whatever the calculation is. It's trivial. We've covered so much, and there's a reason we have to cover so much, is this course is called like Intro to Programming, Intro to Computer Science, whatever it's called. And it starts, assuming you know nothing, and we have to cover everything. Because this course doesn't really, this course is like teaching you how to pick up a pencil and put it to paper. That's not to trivialize the stuff we've done in the course. We've had to learn a lot, and this course isn't easy, is it? You've had to learn a lot, and it's not easy, it's hard. And now you are so well prepared. You can start writing programs to solve problems. Whether you never take another computer science course, you could write a lot of scripts to do a lot of data processing for you in your future pretty easily. Now, obviously, you've taken 1 semester of a computer science degree, so you're going to learn a hell of a lot more if you take more courses. But we've learned how to put pencil to paper. We haven't learned anything interesting yet. Not to say stuff we haven't done hasn't been interesting, but you don't even know what interesting is. Things start to get really fun and a lot more interesting as we go. I'm not saying this to trivialize what we've learned. In fact, I'm saying that kind of like the opposite. What I'm saying is you've had to learn so much in the last 3 months in order to be prepared for next semester. And you did it. You made it. This course tends to have like a remarkably high drop rate. Not at St. Effects, I just mean in general. Right? Because it's not easy. It's quite difficult. And you made it. Good job. But obviously you didn't make it here understanding 100% of everything you've done so far. If you have, well done. If you haven't, you're normal. So let's take a moment. So we covered output and input, and we kind of talked about how like input and output are not they're kind of like special. We talked about values, variables, and types. So you can have a value, you can store it in a variable, and that value has a type. Is it an integer? Is it a float? Is it a string? Statements and expressions, well, that's just like calculating an expression, A plus B. A statement, like your if statements, whatever. Changing types, okay. Functions, we learned how to write functions. We learned some introduction propositional logic, which we kind of learned that we didn't need to learn. We already were aware of it, we just never really formalized it. Remember, that's when I was asking things like, am I wearing a hat and shoes? What would you say? False, of course, because it's not. That's stuff you're already aware of, you just didn't really have a name for it. And then with that, we learned like if and else. We also learned a little bit about testing your code earlier in type hints. Remember, type hints are important because it helps the programmer understand, it helps the user of the code understand what the types of things are, what should be expected you get back from a function. But they're not necessary. And we learned about the assertion tests early on. And we took the time to really spend, we spent time on testing because, writing a function, I don't give a shit if you give me a function for a problem if you can't demonstrate to me that it's correct, right? So the testing is a huge part of it. Testing can feel painful, but remember, it's not writing the function and then testing. It's writing the function and testing go together. Like that, you have to put them together. Otherwise, there's no way you can convince someone else that your code is correct. If else, putting things together. This was the example where we did that car rental thing. How we saw an example of, even that early on, we were able to start solving some problems, based on a car rental agreement and how far someone drove, how much would their bill be. Then we learned about loops. And of course, there were mainly two different types of loops. There were your for loops and then your while loops, right? Your while loops are your more general purpose loop. While some condition is true, it's like an if, but it'll keep running while that condition is true. Do something. And that condition can be anything. That condition can be like a counter condition. It could just be, well, the input was correct or not correct, whatever you want. The for loops were a way to iterate over a collection typically, or if you really wanted to loop for a specific number of times, you could say like for I in range 10. That would loop 10 times. So we saw the two different loops. Strings and objects. So we then hit strings. And at this time, we had been using strings a lot, but we never really spent the time to really focus on how and why strings were a little different than your integers and your floats, right? Because strings, it's kind of like a collection of information. Like the integer 17 is 17, but a string, like the string 17, is the symbol 1 followed by the symbol 7, right? So it's kind of like a collection of information. You might say, well, 17 is 1, 7. Well, that's how we represent it, but the value 17 is just 17. It's more abstract than the symbols on the page, right? But the string 1, 7 is the string 1, 7. And we learned about objects, how, the strings actually had some methods associated with them. It was functionality, but the functionality was associated with a specific string, right? Remember, we could tell a string to split. Remember? That was a method. Split is a method for a string. We tell an individual string to split. So that was a method called on the individual string. It wasn't like a function call. What else? And then the big thing here also was that strings are immutable. Immutable means once it's created, it can't change. Now, if I have a variable that references a string, if I have a variable called myString, and it's referencing a string A, B, C, D, E, F, G, I can change what the reference variable myString references. I can change it to another string, X, Y, Z. But the point is that string, A, B, C, D, E, F, G, exists. And that string doesn't get modified. Remember, that string isn't stored in the variable, it's a reference to it. So I can't go in and change the values, like the characters in that string. It's against the rules. Once the string's created, it's set, it doesn't change. And we saw the value immutability, or in having things immutable, is if it can't change, we don't need to worry about the values of those objects changing. We don't need to worry about the state of it, which is kind of nice. Then we talked about lists, and how lists seem to be like a generalization of strings, but instead of just like a sequence of characters, you can have a linear sequence of whatever the hell you want. You can have integers, characters, strings, other lists. You can have lists and lists and lists. You can do whatever you want, but the lists were mutable. You could go in and say, my list at index 7 is 17, and then 2 lines later, my list at index 7 is 18. You can go in and change it. In lists were objects as well. They had methods. You could append to a list, and it would modify that list that you told to append. And then we spent some time talking about references and aliases. Raise your hand if you're still admittedly a little bit like around references and aliases. A couple people. So you're normal. This is something that's probably going to bite you for a while. I will make, this is a common error programmers make, whether you're a new programmer or an experienced programmer. I make this mistake every now and then as well. I made this mistake yesterday morning by accident. I wanted to have a list of lists, size 9. So of course, in my code, I did this, right? I said, started with an empty list, but then I wanted to have lists in it, and I'm times 9. Right? So now I have a list with seemingly 9 empty lists inside of it. So if I want to append to one of these lists, I say, okay, at index 2, dot append 99, and then at index 6, append 101. Right? So what I want to do is I want to go to the list at index 2, so 0, 1, 2, and append 99 to this, and then go to index 6, 2, 3, 4, 5, 6, and append 101 to it. And when I call run, suddenly I have 9 lists of 99 and 101. Why? Who can tell me what happened? They're all referencing the same list. So I create an empty list with a list in it, right? Who can tell me what I just said that was wrong?
Well, the list isn't empty. It has a list in it.
Well, okay, so this is a list, and inside of it, I wanted an empty list. So inside my list, I have a list, right? Wrong. What do I really have in there?
A reference to a list?
Bingo, a reference to a list. I said, okay, my list, you're a reference variable to a list, and inside you is a reference to some other list somewhere. And then when I multiplied it by 9, I just multiplied the reference to that one same single list 9 times. So I now have 9 aliases to the same one single list. This issue of aliases and whatnot are going to bite you. This literally happened to me yesterday morning. And I spent 5 minutes going, what the hell? This doesn't make any sense. What's going on here? And then, oh my God, I can't believe I did this. Because it's going to happen. You're going to make this mistake. Python is a language that I feel makes making this mistake easier than other languages. So Python, with its flexibility, gives you the flexibility to make this mistake pretty easily. In other languages, it becomes a little bit more obvious about what's a reference and what's not. And in some languages, you actually have variations of the types to specify that this variable is holding an integer or this variable is holding a reference to an integer. There's actually different formats for how you write it. For example, in a language like C++ or C, int a equals 7, int b equals a. I could write something like this in a programming language like C++ or C. What this says is, on that first line of code, I say, create an integer variable called a and assign it the value 7. In a language like C, C++, Java, like we'll cover next semester, they're strongly typed languages, which means if you ever make a variable and you want to store an integer in it, you have to tell that variable you're an integer when you create it. So in that first line of code, I'm declaring the variable a, and I'm assigning it the value 7. The next line of code, that's not empty, is saying, okay, I'm making a variable b, but its type is not an integer. Its type is what we call a pointer to an integer, a reference. So it's not going to hold an integer. It's going to hold like a memory address of an integer. And then a is 7. This ampersand, if you put an ampersand in front of the a, it says, don't tell me what's in a. It means tell me the memory address of a. So this would say, create an integer pointer called b that points to the memory address that a is in. So there are extremes all over the place on how you can have control over the data and what is in that data, and what's a reference, and what's the actual data and whatnot. In different programming languages, there's a lot of different ways you can do it, different levels of control you have. This is kind of an extreme end of control. Python is like, yeah, do whatever you want. With this, you're not going to make the mistake of saying, well, what's stored in A? You go, it's an integer, because it says it's an integer. What's stored in B? Well, it's an integer pointer because it says it's an integer pointer. In Python, if I have just something, if I don't have these types here, now obviously you can't do syntax like this in Python. But in Python, without the types there, it becomes a little easier to make that mistake. In Java, that we cover next semester, it's a little easier to not make the mistake than it is in Python. Java makes it easier to know the difference between what's a reference and what's not, because it's very clear about what the difference between a primitive type and an object is. Anyways. When I have an object, if I create one object, I can have as many pointers, as many references to that object as I could want. I can make an instance of you. Now everyone in the room point at him and keep pointing at him. Do it, point. Come on, do it. Point, there you go. There we go, see? Now we're all referencing you. We have a hell of a lot of aliases pointing to the exact same one single individual object. Right? We are all the references. You're the one actual object. But point to yourself. There, right? Because you have self-reference objects.
Wait, what?
But if you're an object, objects always have that self-reference that just points back to themselves.
I'm an object. But if I'm not an object,
You are an object, but you have a reference. Part of you is a reference. Whatever, I'm being silly. Okay, tuples, dictionaries, and sets. Tuples, kind of like lists, a little less flexible. Dictionaries, they're interesting. They're kind of like a list, but it allows you to index it with whatever, really. Sets, they're interesting, but, they have their use cases. Spend some time on debugging, a little bit on file I/O, how to read from a file, how to write to a file if you really want. We talked a little bit about exceptions, and remember, exceptions aren't errors, necessarily. They're just exceptional situations, and the whole point of an exception is, if I'm writing code today that you might use tomorrow, and something funny happens, like if you tried to divide by 0, what should my code do to solve your problem that you are trying to solve using my code? Well, I can't possibly know what to do. Should your code immediately stop running? Should it ignore it and carry on? Should it try to do the operation again? I don't know. But what I can do is I can throw a message to you. I can create an exception to let you know that something funny happened that's out of the ordinary. And then you can take that exception and manage it how you want. If you want your program to crash, well, if you see that exception, you crash. If you want your program to carry on and ignore it, then you write the code to do that. But the point is, I make an exception that I give you, and then you deal with it however you see fit. Then we hit objects. Objects were kind of like, I would say, how do I word this? Objects weren't building on what we had already learned. It was kind of like a paradigm shift on what we had been doing. Because remember, all of the code we wrote in our methods for the objects was all relatively simple code. Think of the assignment, the country class. The only method you really had was population density, right? So, I mean, that was just a division. It wasn't overly complex. Add for your country catalog wasn't bad. You just appended it. Index, there are all these different things you could do. They weren't overly complicated. What was weird about objects was all of the extra new rules and syntax you had to follow for the objects, right? For the classes that you write. That's where objects got weird. But with a little bit of practice, they probably weren't too bad. Raise your hand if when we first started learning about classes and objects, you were like, oh shit. Raise your hand if after a little bit you're like, okay, it's not that bad, right? You could still be like, I still don't like them. Fine. But once you get used to that, just the syntax you have to follow, you're good to go. Honestly, when I first started learning classes and whatnot, so when I started learning programming, I learned in Java. I didn't learn in Python. I learned with Java. And in Java, everything is part of a class, whether you like it or not. Now, just because it is part of a class doesn't mean everything needs to be an object. But everything, and you don't have to do everything very object-oriented-ness, but everything is a class, meaning all that, like there's a lot of what we would call like boilerplate code for your class, right? There's a lot of code you just need to have to make your class, right? You need to say like class, its name, you need your def init, everything needs to have a self, all of the attributes, all the fields for the class need to start with self. If you're ever calling about that, start with, there's a lot of that stuff going on. I would call that like boilerplate code. Code that you just need to have them. I would say for 2 years, if you sat me down in front of a computer and said, all right, start writing code, I wouldn't be able to do it. If I didn't have an example of the boilerplate code right next to me. Because I didn't spend time remembering that stuff. And that might give you a sense of what's important and what's not as important. Syntax, not overly important to have memorized. Obviously, you're going to memorize the important bits because you just use it so often. But after a little while, the things you write less often, sure, it becomes a little bit more natural. You just happen to remember it. But if you're ever sitting there forgetting, like, what's the syntax for a for loop again? Just Google it, right? That's all you need to do. So the syntax isn't really that critical. What's critical is that you know what a linear search is. That's important, There's the syntax and then there's the actual, algorithms. There's the difference there. So we started with objects. They started very simple. What was it, a circle? And then we made spheres. And then we had spheres interacting with other spheres. We asked the sphere how far away it was from another sphere. Great. And all of those objects are what we would call plain old objects. They are just basically a container for information. That might have some built-in functionality as well. But it's a nice way to encapsulate an idea. It's a plain old object. Then we hit data structures. And data structures where things got a little bit more complex, right? Because with the data structure, it wasn't like, oh, we just have a plain old sphere object. We have a collection. The data structure was a collection of objects. And that's where things got a little bit more sophisticated, a little bit more complex, because the class just wasn't just storing data. The class's job was kind of like managing where and how the data was stored and how it can be accessed and manipulated. So it got a little bit more complex, but at the end of the day, your lists are data structures. You're used to them. Dictionaries are data structures, sets are data structures, tuples are data structures. Everything in your code is either going to be like an algorithm or a data structure. And really the data structures are built with algorithms. But, there's data structures and algorithms. You know how to write your own algorithms? You know how to create your own data structures now. You've got it all. Talked about unit testing. Now unit testing, we got to a point where we needed to hit unit testing because our Sherson tests kind of like lost their oomph because our code got more and more sophisticated, more and more complex, that we needed a little bit more oomph to test them properly. So we learned the unit tests. Now, the good news about unit testing, raise your hand if you're in 162 next semester. Really high, I want to see. Okay. The good news about unit testing is I would say, a lot easier to do in Java than in Python. One of the big criticisms Java has is it's a very verbose language. There's a lot of boilerplate code. There's a lot of, it's verbose. You'll see very quickly. But with that extra verbosity, if that's a word, it actually gives you a little bit more control, which is really nice, so you'll very quickly learn to appreciate it, but it is more verbose. So there is that level of extra verboseness in Java, but the unit tests I find easier to write and work with in Java than I do in Python, just because, just as a heads up. I will also say unit testing collections, like unit testing data structures, is very difficult. And I gave you the unit test for the assignment, but how many unit tests were there for the country catalog? 60. 60 was 60-ish?
There was, pretty sure it was
60, great. I believe you, I just don't remember. Yeah, a lot. And how many were there for the country class?
25, 30.
Oh, I don't even think it was that much, was it?
like 5.
Country was like, yeah,
It was small. Writing tests for your code is typically more similar to what the country class would look like. You just test the functionality of that. Data structures, pain in the ass to test. Because there tends to be a lot of functionality going on there. And a big thing is data structures are stateful. They're mutable. You can change the data in them. So there's a lot of testing that needs to take place to make sure everything's the way it should, because you need to test okay, it's like this. Now what happens if you add and remove and add and remove? How does it look like now? And so on and so on and so on. When you have a mutable piece of data like your country class, you don't need to bother checking what if someone changes the name? Is its name updated correctly? Well, you don't do that because you don't allow someone to change the name. It's private, right? You leave it alone. A lot easier to test. Collections, there's a lot going on there, and they're mutable, so there's a lot to test. So they're a pain in the ass to test. If you're looking at those going oh man, I don't like testing, well, that's because you're looking at a collection set of tests. And those are a pain, and everyone agrees they're a pain. Experienced programmers go I don't want to test collections, they're a pain in the ass. because they are. But even then, I would say writing tests for the collections in Java, just by some of the features like Java gives you for unit testing, is a little easier, I would say. Searching and complexity. That's where we talked about searching. So we talked about a linear search, and that's where I asked the question, if I had n things in my list, and I wanted to find if a given element exists in that list, how many must I look at to guarantee I find that thing or not? Answer. Oh, come on. N? Yeah? Of course. But we saw that other search, that binary search. If I had a list of size n, does anyone here remember? This is a reach. Does anyone remember how much work I would have to do in order to guarantee I find that thing or not with the binary search? It wasn't n. It was a hell of a lot less than n.
It was n times n minus 1 divided by 2, I think you said?
No, that was when you're thinking of the sorting algorithms. You're thinking the sorting algorithms.
The n log n.
That's another sorting algorithm. That was like heaps. That was like merge sort. The binary search is log base 2n. If I double the size of the input for a linear search, it takes twice as long. If I double the size of the input for a binary search, it takes one more unit of work only, by the nature of the log. But there was a giant catch on the binary search. Who remembers what the catch was for the binary search?
Data needs to be sorted.
The data needed to be sorted. I needed to be able to go like, okay, is that what I'm looking for? No? Do I need to look over here, or do I need to look over here? And if it's sorted, if I'm looking at the data 77, and the thing I'm looking for is 40, I know it must be over here, because it's small. And then we looked at our sorting algorithms. The big three that we looked at were insertion, selection, and bubble. Insertion and selection were kind of similar, and bubble was the one where you're always comparing adjacent things and you swap them if they're overborn. But we also kind of learned that although they're intuitive, they're ones that you've probably done, they're kind of slow. And then we briefly talked about one called merge sort, which was a little better. And that had a complexity of n log n, where the other ones had n squared, n times n. But those two topics are perhaps more appropriately placed in next semester's course, so don't worry too much about that. So that's the summary of what we did. We did a hell of a lot. Was there any topics we covered that still to now, you're still left scratching your head a little bit about, that you have any questions about, that we can cover right now? If I get nothing, we'll just leave. Or I'll just leave, you could stay. I don't really care. All right, great. You all know everything. Fantastic. All right, I'll see you all